Today we're going to talk about Hammond's postulate. Hammond's postulate is, I think, an opportunity to really delve into how structure relates to energy. Now, Hammond's postulate, if you were to look it up, in fact, I encourage you to pause this video right now and go just look up Hammond's postulate. You'll see that the definition is pretty complex because it's really a foray into the physical organic, so the physics of organic reaction mechanisms, and how energetics in the physics realm and electron movement and electron position ends up relating to structure and the actual product, and also the intermediates and the transition states between. Now, that gets pretty complicated, but in reality, I think it can be simplified quite a bit. So that simplification, I don't think takes anything from Hammond's postulate. It actually shows you the power of Hammond's postulate and how it relates to many things in the world around us, I believe. So let me show you, starting with a really simple physics example, and then we're going to go into the organic, which can be a little more complicated, but if you understand the physics example, it's not that bad. So let me show you using a really simple prop, like my kid's toy. So my kid has this little toy car. Now here's the question I have for you. What has higher energy? If my kid's toy car is here, or if my kid's toy car is here? Well, you should all answer here, right? I used to ask my students when I taught physics for years, if I hold this book high above your head, do you want me to drop it on you? And people say no. And I would say, why? Well, because it's obvious to us that a large object lifted high has a lot of energy, right? So its position gives it energy. Those of you who've taken physics, right, it's just potential energy. So let's look at that on a simple diagram. Let's say that I have an object like this pen and I graph its energy. Is there a relationship between its position and energy? Well, of course. As it gets higher, and this position is in the y-axis, it's up and down, right? As we lift something higher, it's going to have more energy. All right, there's a direct relationship there between its position and its energy. Well, let me ask a question now to draw out Hammond's postulate. What if I have a position right here, and I have a position here, and I have a position here, okay? Which ones are closer together? Well, these two are closer together. Which one have the most similar energy? Well, it'd be the same ones, right? Because if it's closer on the line, it has a more similar position and a more similar energy. So we're seeing here that position is inextricably tied to energy, right? If I have the pen here, here, or here, which energies are closest together? Well, these are. Which positions are closest together? These are as well, right? Or yet another example, if I took a spring and I stretched it out, and then I stretched it out a little more, which two have the most similar energies? Well, I would argue these two have the most similar energies. Which have the most similar structure? Well, in the same way, those two have the most similar structure because that structure of the stretched out spring relates to energy. By the way, I like to think of bonds oftentimes as springs, right? Bonds actually vibrate and stretch. And as they stretch out, they're actually gaining energy and they snap back together. And if you stretch them too far out, eventually that bond can even break, right? So springs and bonds are very similar. In the same way here, if we have this bond right here that eventually breaks, right? What position of the bond is the closest to that? Well, it's this position where it was about to break and where it had almost as much energy as the bond took to break it, right? So we understand that position and energy are inextricably linked. Now let me ask you a question right here and we'll get to the bottom of this. If we look at this reaction energy diagram, don't hate me for not labeling the axis, but I think you're used to this right now, right? We have energy here. which actually I will label energy because it is very important for our discussion. If you have energy here on this axis, and here you have reactants where A and B are bonded together, and products where A and B are broken apart. Now, as you can see, this is a very endergonic or exergonic reaction. Answer, and then I'll go ahead and give you an answer. We'll see if you're right. Yeah, it took a lot. It didn't give off as much energy, right? The the products have more energy than the reactants. They've absorbed that energy, right? So this is a very endergonic reaction. Now, let's go ahead and look. We have a bond AB here, and we have a bond that doesn't exist here. What does the activated complex look like? Go ahead and draw it real quick. All right? Now, what you should have drawn or should be drawing is A and B with a dashed line between them, right? Because the bond is in the process of breaking. Now, here's the interesting question. And pause it, think about it for a little, apply the energy and position are related idea, and try to answer this question for me. Is this bond mostly broken, exactly halfway broken, or not broken quite at all yet, right? So think of it as the bond could be just starting to break or could be almost done breaking. My question is the bond just starting to break, halfway through breaking, or almost completely broken at this point? So pause the video, think about it, write an answer down, and in fact try to answer why. Remember, energy is a huge hint to you, and the fact that position or structure is very related to energy. So go ahead and think about that. All right, so you should have noticed that actually, if you look at the energy here, this activated complex is very similar or closer in energy, right, to the product than it is to the reactant. So we know energetically it must look, that activated complex must look a lot more like the product structurally, right, because its energy is so much like the product. Look at our old examples with the height of things or springs breaking and try to make a connection here. I know it's a little abstract, but if you make that connection, you're going to understand how we know that this bond here is mostly broken, right? It's almost all the way broken because its energy is very similar to the fully broken form. And remember, we said this was an endergonic reaction. So let's look at one other example real quick. All right, so if you look here, you'll notice that we have not the same reaction, right? It's still AB, but it's actually a different reaction. And in this case, is it endergonic or exergonic? In this case, the products have lower energy than the reactants. They've released energy. So this is exergonic. Now, in this exergonic reaction, answer the same question for me, and let's see if you can apply Hammond's postulate. Is this bond mostly broken, half broken, or mostly unbroken? So go ahead and pause. Answer the question, and please write an answer as to why you think it is. Remember, Hammond's postulate, use the energy. You need to be able to explain why you believe it. You can't just guess which one it is. All right, so what you should have gotten here is you should have noticed that the reactants here are very similar. These energies are more similar than this energy is to the products. So this means that bond is still mostly unbroken because the energy is more like the reactants where there is a bond formed, right? So this shows us that position and structure is related to energy, and just using energy diagrams we can figure these out. This is why you'll learn from Hammond's postulate that in exergonic reaction, the activated complex looks more like the reactants, right? Because their energies are more similar. in an exergonic. Whereas in an endergonic reaction, the activated complex looks more like the products structurally. So this is going to be really important moving forward. We're going to apply and use this idea throughout this semester and a future semester. So please make sure you have Hammond's postulate down pretty well. It's an important concept.